Good morning everyone. Welcome to another lecture on computer organization and architecture. So this is a recorded lecture. The objective of this recording to give you better clarity on audio wise and seeing the slides and so on. I was told that some of you do not have proper connectivity to listen to live classes. So this will be a solution for that. So after watching the video, we will have a discussion session so that you can clarify your questions. I request all of you to keep a pen and paper while watching the video and note down the terms that you understand and that you do not understand so that you can ask questions once the video is over. So that discussion will happen in MS Teams in live mode. So let us continue the lecture. We were studying the MIPS instructions for various purposes. We have seen different types of instruction formats, different instructions for different purposes and so on. So today we will see some more variations of that. All these are required to properly understand the design decisions taken by the MIPS people. So we have immediate operands coming as part of the instruction. You can use that immediate operand for a negative value and so on. So next is the variation of load instruction. So load is you have what is known as an offset and a base address form. So in this slide you will find LW, RT is the register that get loaded, and SIMM stands for signed immediate, and RS. So this signed immediate tells you the offset sign, whether it is a positive offset or a negative offset. So if you have a value in the base register, if you add the offset, you get the effective address. The value that you are adding to the base register can be positive or negative. That is what we represent using signed immediate. So next instruction is loading the register $1 with the content obtained by adding 40 to the base register. Okay. So that is how we have to understand. Next one is loading into the upper half. LUI, load upper immediate. And here also this is signed immediate. You can load the upper part of R5. So upper part means if you R5 is a 32-bit register. So upper part means the higher order bytes in the R5. So a register can be viewed as consisting of 4 bytes, B0, B1, B2 and B3, where B0 is the lower order byte and B3 is the higher order byte. So in this instruction we are moving the signed immediate to the upper part. Okay, so upper part is shifting the content to the left by 16 bits. So in all these slides you will find SIMM. SIMM stands for signed immediate. Next, let us look at the ways in which control instructions are working, or instructions that changes the flow of control is working. So we have compare and branch instructions. They work is dependent on the PC value, or they all rely on the PC value to find the target address. So this type of addressing is known as PC relative branches. Now if you look at the instruction, RS and RT are compared, and based on the comparison you are modifying the PC. So look at the first instance, branch on equal to RS RT offset. So if RS and RT are having the same value, then we will be using the offset value to modify the PC. So that offset is a signed value. That means you can add the offset, which could be a positive or negative value, resulting in a branch which is going forward or backward. If the offset value is positive, you will be branching forward, and if the offset value is negative, you will go back to some addresses behind the PC. So that is how they are working, BEQ and BNE. So please understand that the offset in branch instruction is a signed value. Okay. Now, most of the comparisons will be against 0. We'll see the soon. So these instructions, they take less arguments. There is only one register argument. So this will be compared against 0. BLE is a branch if less than or equal to 0. Greater than 0. This is less than. Then branch LD, branch if less than. So these are self-explanatory. They all do the same operation to the PC. They modify the PC with the branch. So you can make note of these instructions. From the acronyms itself, it is clear. BLTZAL means branch if less than 0 and link. So this will be used when there is a procedure call which has to be made on a conditional basis. Now coming to the MIPS jump. So jump is using an absolute address. It's not a offset kind of stuff. It's an absolute address. You provide an address as part of the instruction. Whereas in branch you gave an offset. You have to be very clear about that. So in jump, what we do is we take the absolute address and replace the PC. There is no addition or subtraction that is happening to the PC. We are just replacing the PC. So this requires some more understanding. So one instruction is J immediate. You are giving the immediate address, and to that you are jumping. Next, jump and link. This is used when we have a procedure call. JR, that is, keep the address in a register, and that register will be used for jumping. So in this case, R31 is linked to the PC value is taken there because you want the return address. So here PC is replaced with whatever content is there in the RS register. Okay. Now JALR, jump and link register. So here you are jumping to the address specified by RS. Okay. And you have to come back to that point so that you can resume after the procedure execution. For that, we need to keep the original value of PC before replacing it. That is kept in RT. So you look at the operation, we take the old PC value and keep it in RT and replace the PC after that with the value given as part of the instruction. So the program will jump to the location identified by RS. There you will have a procedure, and that procedure will execute, and you will come back to the point again by reloading the PC back from RT. Now, these are the two important points. All gems are absolute. That means you give the address as part of the instruction itself. Now, no addition, subtraction, etc. happening with the PC. Whereas all branches are relative to PC. You give an offset, that value will be added or subtracted to the PC. So this will be a signed offset. So when you operate with a signed offset, you get the result of addition or subtraction. Now let us look at how this 26-bit instruction, which is coming as part of the jump instruction, is converted into a 32-bit instruction. And also if we use a 16-bit signed offset, what is the maximum limit that you can jump as part of a branch instruction? That will also we will look at. Now, how do we, that is what we are going to see now. How do we compute the branch target address or the target address? So in the case of a PC relative addressing, the instruction will be a I-type instruction. We know that I-type instruction has got 6-bit opcode, 5-bit RS and 5-bit RT and 16-bit signed offset. So in this 16-bit signed offset, 1 bit, that is the MSB of that 16 bits, will be a sign bit. It will tell you what kind of value it is. If it is sign bit is 0, the value is positive, and sign bit is 1, the value is negative. So out of the 16 bit, 1 bit is devoted for the sign. So remaining 15 bits are there for you to decide the jump, the branch address. So you have plus or minus 2 power 15 bytes from the current instruction you can jump as part of the PC relative branch. So new PC will be equal to PC plus 4, which is the updated PC value, plus signed immediate left shifted by 2 bits. So why do we left shift? The objective is to convert the address given into a word aligned address. So left shifting by 2 bits is same as multiplying by 4, and we know that address becomes word aligned if it is a multiple of 4. So whatever value we give as part of the instruction in the place of offset gets multiplied by 4 to convert it into a word address, and that is added to the PC to get the new PC value. So new PC value is equal to PC plus 4, which happens immediately after an instruction fetch. To that we are adding the signed immediate multiplied by 4. So how do we convert the absolute address which is given as part of the jump instruction into a 32-bit address? That we will see in the next video. That is, J-type instruction gives us 26 bits. So the question before us is, how are we going to convert that 26-bit absolute address into a 32-bit quantity which will replace the PC? So that we will see in the next video.